At absolute maximum physical exertion, the human engine pushes towards its red line, processing oxygen at the highest possible rate to sustain top speed. This physiological ceiling is defined as VO2 max, the maximum volume of oxygen your body can utilize during exercise. Because oxygen fuels aerobic work, VO2 max serves as a definitive baseline measurement of total running fitness. Yet a marathon is a sub-maximal, steady-state endurance event, a race prioritizing energy conservation over 26.2 miles. This creates a divergence in training data. On the left, marathon success requires a flat, sustainable output. On the right, VO2 max intervals generate steep, unsustainable physiological spikes. This gap presents a contradiction. Why introduce a high-intensity, maximum-effort protocol for a race demanding energy conservation? The strategy relies on adaptation. Exposing the system to maximum capacity forces cellular and biomechanical changes, improving submaximal performance. These intervals construct a biological engine that makes slow speeds metabolically cheaper, shifting the focus from top-end speed to systemic efficiency. This process starts with the aerobic pathway. Oxygen moves from the lungs into the bloodstream, eventually reaching the mitochondria within the muscle cells. In untrained runners, this pathway has a strict volume limit, acting as an energetic bottleneck that restricts total work. Training at the VO2 max limit acts as a stressor, structurally expanding this pipeline and widening the pathway for oxygen delivery. As the body processes a higher volume of oxygen, it gains the capacity for a higher total energy output. This expanded capacity results in a higher oxygen utilization ceiling, which directly correlates to a higher absolute maximum running velocity. While a higher top speed is a clear benefit, it primarily serves as the baseline required to trigger deeper marathon adaptations.
We can see the second adaptation by observing the physics of a runner's stride. At relaxed paces, runners often exhibit vertical bouncing or lateral swaying. These movements represent energetic leakage. Vertical oscillation and side-to-side movement require muscular force, but they do not contribute to forward motion. Reducing this leakage improves kinematic efficiency, the measure of how effectively the body translates energy into purely forward propulsion. High-speed interval training introduces strict mechanical constraints. As speed increases on this wireframe model, the body eliminates wasted motion. At extreme velocity, posture tightens, the stride angle sharpens, and energy is directed purely horizontally to maintain the intense pace. To hit these prescribed speeds, the body must find the most direct path of propulsion. Energy diverted into vertical or lateral motion results in a failure to meet the training target. Over time, the central nervous system habituates to these patterns. The most efficient movement becomes the default neurological path. These optimized mechanics carry over to endurance efforts. The tightened form learned at maximum speed remains in place even when the runner slows down to marathon pace. High-speed intervals serve as a biomechanical calibration, stripping away wasted motion to ensure marathon pacing is mechanically efficient. Beneath the mechanics of the stride, we must examine the microscopic architecture of the leg muscle bundles. This determines neuromuscular economy, the specific amount of muscular energy required to maintain a forward speed over time. At standard marathon pace, 70% of the muscle bundle in this cross-section must constantly contract. VO2 max intervals severely load these fibers. The cells respond through hypertrophy, visibly thickening to increase their individual strength and power output. When we re-examine marathon pacing with these stronger fibers, the recruitment math changes. Because each individual fiber is now stronger, a smaller percentage of the total muscle bundle, only 40%, needs to fire to achieve the same speed. Using fewer muscle cells to perform the same task reduces the total work performed by the leg muscles. This drop in muscle recruitment leads directly to a decrease in continuous metabolic energy expenditure. This energy savings accumulates over the tens of thousands of individual strides required to cover 26.2 miles. By increasing individual muscle fiber power, VO2 max intervals reduce the total metabolic fuel required to sustain the same distance. This evidence resolves our initial paradox. The marathoner is not wasting energy on sprints, they are upgrading the system. Looking at our marathon pacing line again, we see improved neuromuscular economy and kinematic efficiency. A fuel gauge depletes much more slowly at the same pace. The goal isn't preparing the cardiovascular system to survive a marathon at 100% effort. Instead, it is a tool used to elevate the physiological floor of the entire mechanical system. Maximum oxygen expands the work ceiling. High-velocity mechanics increase muscular power, lowering the metabolic cost per step. These structural adaptations require the extreme stimulus of maximum capacity. They cannot be triggered by submaximal jogging alone. Developing the efficiency required for elite endurance requires the specific structural adaptations only triggered by training at maximum capacity.